So in this lecture, we're going to talk about positioning the camera in the scene. Specifically, we will talk about two different viewing, a classical viewing, which is what you may have done in your engineering graphics. I'm going to have slides for this. I may not be able to cover that in the lecture, but I will ask you to go through these slides as additional material. What I am going to talk about is computer viewing. So I'll begin by comparing computer viewing with classical viewing and talk about what kind of assumptions we have the luxury of making since we are dealing with computer viewing. The main focus of today's lecture is to introduce the mathematical basis of projection transformations. The reading for this lecture and a little bit of the next lecture is from chapter 4. Let me begin by just talking about the classical viewing in terms of contrasting it with computer viewing. By classical viewing, again, I mean the kind of views that you may have seen in your engineering graphics class. So for example, the plan view, the elevation view, orthographic projections, things like that. Primarily, I want to contrast two different types of viewing, perspective versus parallel. So in computer graphics, we do not distinguish between or rather the pipeline does not distinguish between the different kinds of projections. It treats all the projections the same way. They are all matrix transformations. So the differences is really implemented by you, and it's all done within the same pipeline. In contrast, in classical viewing, you would have learned different techniques for each type of projection. For example, you would have distinguished between parallel projection and perspective projection. You would have talked about different procedures for each type of projection. Let's look at these two for a bit. Perspective projection is what we have seen when we talked about image formation. So this is where we have a COP, the center of projection, and we have projectors. These are the lines from the object that form the image on the projection plane. A parallel projection is merely one where the center of projection goes to infinity. And so what we are left with is a direction of projection, DOP. So essentially one can think of parallel projection as a special case of perspective projection. In computer viewing, however, we would not take this viewpoint. We would find another way of combining parallel and perspective projection within the same pipeline. So let's start talking about computer viewing now. There are three aspects of the viewing process. Unfortunately, none of that is implemented in our pipeline, at least in the modern pipeline. But let's talk about them because you will be in charge of implementing these steps. The first is to position the camera. So this we would do by setting up a matrix, a transformation matrix. You need to select a lens for your camera. We would do this by setting up a so-called projection matrix. Next, we would have to do clipping. So essentially decide what objects are visible to the camera. So we set this up by specifying a so-called view volume. So with most APIs, and OpenGL is no exception, there are default values for all these steps. The OpenGL camera does the following. Initially, by default, the object and the camera's frames of reference are the same. So we talked about this briefly during the previous lecture also. So here is what it is. So the camera is located at origin and it points in the negative Z direction. The default projection matrix is identity, so essentially doesn't do anything. The default view volume is a cube whose sides are of length 2 and centered at origin. So let's look at a picture. So here is the default projection. So as you can see, the default projection in a graphics pipeline, at least with OpenGL, is orthogonal projection. And here in blue is the default view volume. So you can notice that the origin is at the center of this view volume. It is side length is 2, as you can see, and the axis, so this is something that you may want to remember. The convention is that x axis towards the right, positive x-axis, y-axis pointing upwards, and z-axis pointing towards you or coming out of the plane of the screen. So remember that the camera is positioned at origin and it is looking in the negative Z direction. So if the objects are inside the view volume, you want them to be visible or projected, and objects that are outside the view volume, you want them to be clipped out or removed. So we'll deal with this later. Let's look at objects that are inside the view volume. We would like them to be projected onto the projection plane, and the default projection plane is the Z equal to 0 plane, because remember that the camera was located at origin. Now clearly we don't want objects that are behind the camera to be visible or to be projected. So there are many ways to fix this. A simple way is to move the camera so that the entire view volume lies in front of the camera. Let's talk about that situation first. So again, the default situation is what is shown on the left, where the camera coordinates and the world coordinates align with each other. Now we want to move the camera away from the origin or away from the world coordinate origin. So, and we do that by translating by negative d. Right? So when you do that, what happens essentially is that the objects move along the negative d direction. So in essence, the camera is moving away from the origin in the positive z direction, right? So essentially, in order to move the camera, one has to move all the objects in the negative direction in terms of translation. So of course, this applies to the other transformations as well. Let's look at another example which involves rotation and translation. So let's say that the new camera position and orientation is as shown here. So it's positioned on the x-axis and is looking at the origin. And the way that you can achieve this position for the camera is by first translating it along the z-axis, followed by a rotation so that it goes and sits on the x-axis. So this transformation essentially is RT, T followed by R. However, note that the transformation that needs to be applied on the objects is the inverse of this. So the model view matrix, which is what we care about, is applied on every vertex of the object. So the model view matrix is written as RT inverse. So in this simple case, one can write down the model view matrix. So you can imagine that positioning the camera can quickly become a difficult task if you would want to write down this matrix explicitly every time. So instead, what you may want to do as an application programmer is to define and implement a look-at function. So essentially, this function should form a matrix which essentially is a concatenation of several modeling transformations, right? And this gives you an easy interface to position the camera. So the early OpenGLs actually did have something like this within a library called GLU. Of course, these are deprecated now, no longer available to you. So you may have to implement a function like this yourself, a look at function. So you may want to think about what this look at function will do if you would like a so-called isometric view of the cube. If you don't remember what isometric view is, you can go back to the slides on classical viewing and find that out. So what are the arguments that you would want to give to the look at function? You would of course want to specify the I location, so IX, IY and IZ. You want to specify an orientation for the camera. One way to specify that is to say in what direction the camera is looking. And so the way we specify that here is by specifying the at location. So what point is the camera looking at? So this specifies a vector, right? A vector between the location of the camera I and the at, the gaze point at. In addition to this, you want to specify the upward orientation of the camera, and this is done by specifying a vector called up. Almost all APIs, graphics APIs, have one way or the other to specify a camera position and orientation. So starting from the early days of FIGS and GKS 3D, you have different ways of specifying camera. So you could specify the view reference point, the normal to the plane of the camera and the up direction, or you can specify yaw pitch roll like an aeroplane. You could specify elevation, azimuth twist, or direction angles, and so on. Now, given this way of specifying the camera and how it affects the objects, you may want to think about implementing something like a fly-through or a walk-through in your scene. So essentially you have to apply a sequence of operations that mimic the movement of the camera within your scene. So like I mentioned earlier, the default projection is orthogonal, right? So this is a very simple projection, so hence it's default. So what does this mean? So for points that are within the default view volume, this is what happens. The x and y coordinates are preserved. So the x sub p and y sub p, the projected point, have the same coordinates as the input. The z coordinates get mapped to 0. Right? So that's essentially your orthographic or orthogonal projection. So you can quickly see that this orthogonal projection is along the z direction, which is why z goes to 0. So almost all graphics systems employ something called view normalization. So they would assume that the projection is orthogonal, but the way they would support other projections is by normalizing all other views so that they get converted to the default view. So these transformations that you need to apply, these normalization transformations, they determine the projection matrix and hence allows you the use of the same pipeline for all views. So when you have homogeneous coordinates based representation, this is how your matrix looks like. So M is the projection matrix. You can see how it sets ZP to 0, right? And P sub P is the projected point. In practice, however, what we do is to set M as the identity matrix. So this causes no harm really. So what you essentially do is to preserve the Z values, we just don't use them. And we eventually set the Z value to 0. And preserving the Z value actually comes in handy, as we will see later. So let's talk about perspective projection and the associated matrix. So let's assume that the center of projection is the origin and the projection plane is some z equal to d, where d is less than 0. So essentially the projection plane is in front of you. So note again that the camera is at origin and it is looking along the negative z direction. We have already seen these equations of simple perspective, right? So you may pause and take a look at this again. So essentially your projected points x sub p and y sub p can be computed using similar triangles. So the ratio of x sub p to x is the same as the ratio of the z coordinates. Similarly for y sub p, and z sub p is essentially the distance to the projection plane. So I can write this down in the form of homogeneous coordinates. So in homogeneous coordinates, we get the projection matrix in this form. So Q is the projected point. So note here that the W value, the fourth coordinate for Q, is not equal to 1. So we have to do a so-called division, perspective division. Also note that the projection matrix is not your typical affine transformation. So in fact, in general, this projection transformation is not invertible. So in order to specify your view volumes, again, we can think about some application defined functions. So you could implement these functions on your own within your application program. So having these functions actually simplifies the setting up of your scene. I mean, you could write down the matrices explicitly, but defining such functions and implementing them makes your code readable. So the most common orthographic projection and view volume would be as follows. So you would have your view volume as an axis parallel pipe, and the way you specify that is by specifying the different coordinates. So left, right, bottom, top, and near, far. You can see where these points lie within the view volume, which is shown in blue. So note that in this case, near and far are measured as distances from the camera. This is convention. Of course, you can use a different convention. This was the convention used in the early versions of OpenGL. So we follow them. It's useful to think about how near the near plane is and how far the far plane is with respect to the camera. So next we talk about perspective view volumes. So here you have a center of projection. So the view volume also changes. It's no longer a cuboid or a parallel pipe. It is a frustum. And the way you specify that frustum again is by talking about the near and far planes, right? So these are shown in light blue and dark blue. But in addition, you want to specify the view frustum by specifying the corner points. So you specify the left bottom corner point and the right top corner point in the near plane. This should be sufficient. Specifying the perspective view volume using the frustum is correct, but it's not too intuitive. So an alternate that people use often is one where you specify fewer parameters such as field of view, the angle subtended by the view volume with respect to the center of projection. Of course, you specify the near and far planes. These are important. Next you specify the aspect ratio, right, which is essentially W over H. So these are parameters that are familiar, especially for a photographer. So they are very useful in practice. Let's go back to discussing normalization. So the idea behind normalization is that you don't want to derive a different projection matrix for each type of projection. We already saw 3 different ways to specify your view volume, and we saw 2 different projections. So we want to convert all these projections to the simple case of the orthographic projection from the default view volume. So the question is, what kind of transformations can I apply so that in the end, the only projection matrix that I write down is the orthographic projection along the z-axis from the default view volume. So how does this normalization really help us? Let's answer that question first. So we know that in the vertex processing stage, this is the first stage of the pipeline, we apply model transformations to all the objects. Then we apply a projection transformation, right? So what we would like is both transformations to be non-singular. We already saw that the projection transformation is actually can be singular. It need not be invertible. It could project multiple points to a single point. So we clearly want to avoid this. One way to avoid it is to replace this projection transformation by a normalization transformation. This is what happens in a typical graphics pipeline. This is followed by perspective division, where the homogeneous coordinates go to 3D coordinates, followed by actual clipping in 3D, and then the actual projection, where the 3D coordinates go to 2D coordinates on the projection plane. So applying the normalization simplifies several stages of the graphics pipeline. First, it simplifies the clipping stage. It simplifies essentially the rasterization because of that. And it also allows us to delay this so-called hidden surface computation. We will see that this is a major advantage of the normalization transformation. So let's look at these matrices for normalization for the different view volumes that we saw earlier. The first is for orthographic projection from a cuboid. So essentially we want this cuboid to be transformed to the default cuboid. That's the default view volume. Right? So this is essentially what the normalization would do. Right? So writing down this matrix is not too difficult. It's essentially a scaling transformation, and this is what we have seen in the lecture on transformations. So the matrix would look like this. So we could think about forming the matrix via a sequence of transformations. First, you may want to move your view volume to origin. So the center of the view volume is given by left plus right over 2, bottom plus top over 2, and near plus far over 2. And you want to move that to origin. So hence the arguments to the translation matrix T. So note again that near and far are distances to the near and far plane. So the actual coordinates are minus near and minus far. So after moving the center of the view volume to origin, you want to scale its sides. Again, this is an easy operation, and the scale factors are written here. So we can combine these two to give us our final normalization matrix P. So you can work this out yourself. Of course, the final projection is where you set your z coordinate to 0 via orthographic projection. So the way we do that is by setting up this matrix that we have seen earlier, the orthographic projection. So our P should ideally be T followed by S followed by M sub orthographic. So note again that we typically write accumulate, but this is the reverse order in which the operations are applied. So T gets applied first. So in order to talk about perspective projection, I want to introduce oblique projections first, because this will play an important role in our derivation. So oblique projections are where your projectors are parallel to each other. So you see the lines going from the object to the projection plane. They're all parallel to each other, but the projectors are, they subtend an angle which is not equal to 90. So what this allows you to do is to see the side of the object. So when you project a cube that lies in front of you, the oblique projection will produce an image such as this. So here the cube appears to have been sheared to the right. So essentially, the oblique projection can be considered as a shear applied to the cube, followed by a simple orthographic projection. So here is the equivalency. So the blue, what you see here, is the object that you would like to project onto the projection plane, right? So P is what you would like. So note that the projector is not parallel. I mean, they are parallel to each other. The projectors are parallel to each other, but they are not orthogonal to the XY plane. So they don't, they are not parallel to the Z axis. You can see that easily. What you would like to do is to use orthographic projection, which is parallel to the Z axis, to the Z direction. And the way you achieve this is by first applying a shear H that shears the view volume and then applies orthographic projection. So the shear needs to be applied in two directions. The first is along the x-axis and then along the y-axis as well, right? So the two angles that you see here are the shear angles, theta and phi. So we have already seen the matrix corresponding to the shear by an angle theta. So we need to just write down what theta is here, right? So we've already seen this equation earlier. So now we have the shear that affects the y coordinate as well. So we need to write that down. So we have two shears. Note that that is the reason why you can see the top face and the side face. So this shear does not change the Z values. And the matrix can be written down in this way. So essentially here in this matrix, all I am doing is writing down the two equations that we saw earlier. The projection matrix P can be computed by accumulating the orthographic projection M sub orth. Of course, in general, the after shear, the view volume need not be centered at origin. So you may have to apply the translation followed by the scaling that we saw earlier in order to get the default view volume centered at origin and with side length 2. And finally, you apply M sub orth. So I mentioned that the normalization simplifies the clipping operation. And this is how it does. Note that we haven't talked really about how clipping is implemented, but we understand what clipping is, and that is sufficient for this discussion. The projection matrix, what we have P, right, it transforms your original clipping volume to the default clipping volume. So let's consider what the clipping operation should do. So here is a top view, and in blue what you have is the object, and what we have here, the black polygon, is the clipping volume. This is just the top view, and we have the direction of projection, right? So this means that this line here is the near plane, right? We are looking at only the top view, so I'm not showing the rest of the view volume. We have the far plane. After the normalization, the black view volume should become the default view volume, which is x equal to plus or minus 1, z equal to plus or minus 1. Of course, this is the top view, so you don't see the y equal to plus or minus 1 planes as two separate planes. So here is the direction of projection again along the z-axis. So note that this normalization affected the object, because the view volume is essentially just a construct. There is no physical view volume stored anywhere within your graphics pipeline. The operation that we write down, the mathematical transformation that we write down, is applied only on the objects, the blue objects. So the blue objects gets transformed into this polygon here, which is distorted, but then it projects correctly. That's the idea. Right? So what is the effect of normalization on clipping? So clipping can now be performed with respect to the standard view volume, x equal to plus or minus 1, y equal to plus or minus 1, z equal to plus or minus 1. This is very easy when compared to clipping against arbitrary planes when you have a arbitrary view volume. So that is the benefit. Okay, so let's talk about simple perspective and how will we write down the matrix corresponding to this simple perspective. So what does simple perspective mean? The center of projection is at origin, right? So we see that here, the center of projection is at origin. The near clipping plane is z equal to minus 1. You see that, the first blue square. The far clipping plane is equal to z equal to minus far. So this essentially gives you a 90-degree field of view, right? And the planes that define the view frustum are x equal to plus or minus z and y equal to plus or minus z. You can confirm this yourself. So what is the matrix that corresponds to this? So this is the simple perspective projection matrix. You can quickly see that this matrix has this -1 on the 4th row. The far clipping plane does not appear here at all. This is not surprising. So the projection does not depend on the far clipping plane. The far clipping plane only decides which objects get projected. So let's try to generalize this first so that it can be applied to other volumes. So note here that the projection plane is z equal to -1. Right. So we want to take the form of the matrix that we saw earlier and generalize it first. So just bear with me, this is a trick, but we will see how that gets applied. So we are writing down this matrix N, which looks just like the simple perspective projection. So with the -1 here. But instead of a 1, we have an alpha and then we add a beta in the next entry. So when this matrix gets applied, right, this is what we get. When it's applied to x, y, z, 1, the new point that we get after perspective division is x prime is -x over z, y prime is -y over z, z prime gets transformed in this following way. So note that after orthographic projection, what you have is the desired projection, right? Independent of alpha and beta, if you use N followed by orthographic projection, then you end up getting the desired projection points x prime and y prime. So N can also work as a replacement to the projection matrix we saw in the previous slide. But what is the benefit of N? So just to recap, this is how we are using N, right? We are following N with a orthographic projection, and we show just by explicitly working out the calculation that we do get the perspective projection matrix. So note that this is simple perspective that projects onto the z equal to -1 plane. Now we have the choice for alpha and beta. The way we choose alpha and beta, so we choose these two values. The way we choose this is to ensure that the near plane gets mapped to z equal to -1. The far plane gets mapped to z equal to 1, no matter what the far plane is. And we want the sides of the view volume to be mapped to x equal to ±1, y equal to ±1. Going from x equal to ±z and y equal to ±z, right? So choosing this alpha and beta essentially makes the clipping volume to become the default clipping volume, right? So this is what happens to our clipping volume. You have your center of projection here. Z equal to minus near is the near plane. Z equal to minus far is the far plane. After your normalization transformation, the original object, which is shown in blue, gets transformed into this object shaded that you see on the right. So definitely it is distorted, but the normalization fixes the view volume to become the default view volume. Again, this simplifies your clipping computations dramatically. So this is the benefit of normalization, at least with respect to clipping. So let's see the second benefit of normalization. So we'll continue where we left off in the previous slide. The form of this matrix N is not arbitrary. It was chosen with a lot of thought. It was chosen so that if you have 2 points, Z1 and Z2, in the original clipping volume and Z1 greater than Z2, then we wanted to retain that relative order for the transformed points, right? The reason for this is that we want to make decisions about hidden surfaces at this stage, at a much later stage. So we want to apply our normalization transformation, bring everything into the default view volume, and then since we are doing orthographic projection, we can quickly decide which vertex or which surface should appear and which should not. So in a typical scenario, you want the surfaces that are close to you to appear. So you can use the Z coordinates to decide which surfaces appear and which do not. But of course, Z primes are distorted. The normalization transformation does distort the distances. And this is not a linear transformation for the distances. It distorts it like this. Z prime is alpha plus beta over Z, the negative value. So this distortion does introduce numerical issues. For example, there is a division by Z, particularly if the distances are small. So for small values of Z, you could have a lot of numerical issues due to floating point arithmetic. So this is something that you need to be aware of. So when you have 2 points that are close to you, so the Z values are small, then their projected points could be quite different, and the order may not be preserved simply because of floating point arithmetic. So we do see this in practice, so it's important to be aware of it. So the next, let's talk about the different ways of specifying the view volume. We saw this way of specifying a frustum. This allows for an asymmetric viewing. Essentially, you can have your view volume to be sheared to the right or to the left. So this is not very typical. So typically what we specify is a perspective view volume, which is symmetric. So what we saw earlier was the simple perspective, which was symmetric. But like I said, for the frustum, the view volume need not be symmetric. So you want to apply an additional shear that will bring this frustum to the simpler right viewing pyramid that is symmetric. And then you may want to scale it also to get the normalized perspective volume that we saw earlier. And after this, we know how to set up the matrix to go from the standard perspective view volume to the orthographic view volume. So we know n, that's what we derived just now. Before applying n, we want to apply a shear h followed by a scale. This is if we want to specify a view frustum, right? So you can imagine how you can write or implement any such functions for specifying a view volume, right? So you would have to somehow break it down or convert it into one of the standard forms, and then you will be able to write down an expression such as this. So to conclude, why do we want to do normalization? Normalization allows us to implement a single pipeline for perspective and orthographic viewing. It simplifies clipping because everything is now done with respect to the default view volume. Very important, it simplifies hidden surface removal. We are actually going to see this a little bit more later. So if we use 4D homogeneous coordinates, then it allows us to retain the 3D information that's needed for hidden surface removal and for shading. So with that, we end our discussion on cameras and viewing. So now we are ready to talk about lighting, which we'll do in the next lecture.